Hello, it's Duncan. Dmitry Kandalov and I worked together on the Gilded refactoring a few weeks ago, and came up with a really nice path through that he recently published on his channel. I'll link to that video in the notes below, and if you haven't already, please do watch it, as we found some really nice ways of using IntelliJ intentions to separate out the mess of the Gilded rows update function. The version that Dmitry published stopped too early in my opinion though. His solution has the advantage of simplicity, just using the names of the magical items to select behavior, but to my mind that misses the opportunity to use object-oriented programming in just the sort of situation it was designed for. One of Bob Martin's solid principles that has stood the test of time is the open-close principle. Our code should be open to adding new features, and adding features shouldn't require extensive modification to existing code. In the Gilded Rose kata, we're asked to add the feature of a conjured item, and it's clear this will require a great deal of rework given the existing code. Our mission then is first to refactor in order to make the new item type not a modification, but an addition. That refactor will be a modification, but if we get it right, the new feature will just be adding to the code. Dmitry's refactoring didn't go quite far enough to make that true. It's possible the following version goes too far. So this is the state of the code base just before Dmitry started changing the item class and was cursed by the goblin. And state is very much a relevant word because object-oriented programming was designed to help with managing state in programs, solving the problems of state becoming inconsistent between two different places. Two of the fundamentals in software is state and behavior, and you can see where we are at the moment, those are separated. Our state is represented by this item class that has name and sell-in and quality, and they can change, so it can change its state. Our behavior though is defined by this update function, which takes an item and changes its state. And when I say takes an item, it's the receiver in an extension function at the moment. Now, one of the fundamentals of object-oriented programming is encapsulation, and that means hiding things behind boundaries. But you can see here there's no hiding behind boundaries going on. Anything can come in and change these public properties of name, sell-in and quality on an item. The main place we might see that as a problem is here, where there's a business rule about the quality of an item that is between 0 and 50, but any code can come along at the moment and set the quality of an item to anything it likes. So without encapsulation, the invariance of our software can be broken. So if we were allowed to change item, then maintaining that invariant would be the first thing we'd want to do, and that would mean replacing the setter on our quality with something that maintained it to be in the proper range here. But the rules of Gilded Rose are very clear that we can't change item, and so we're forced into more creative but less satisfactory solutions. Okay, having thought about encapsulation, what about another thing beginning with E? What about expressiveness? Our software is expressive when concepts in our domain or our implementation have a place in our software. Looking at our item update, we can see there are two things happening. One is an update of our sell-in, and the other is an update of our quality. To the extent they have a place, it's because they're separated by this blank line here. Now, Dmitry did extract functions for the two different concepts here, but he did it after he changed the item class. So let's put those back in, and we'll give them names. So what is this? I think this is aging. It's how the number of days that we have to sell it in changes. So we can extract a function that is age. So we've aged the item. And then the second bit here is degradation. So again, we'll extract a method for degrade. And now those two parts of the operation, the two separate bits, have an expression in the software as two separate functions, age and degrade. Now the computer doesn't care that we split this into two functions. It only really matters to humans, and one of the important reasons for this is capturing information when we have it. There's a good example of that down here. This if change is not equal to 0. We might ask, is this required at all? Let's find out by commenting it out and running the tests. You can see they fail, and they fail because Sulfurous has a starting quality of 80. And so it doesn't want to be dropped down to 50 by this coercing. But that begs a question, which is it this change being 0 that's important, or is it being sulfurous? In other words, is this 0 here the same as this 0? If it is, then we could replace this test with if name is not equal to sulfurous, and that would pass the tests. So what we have here is two ways of passing the tests, but if there were other types of items, that would change the behavior of the software. We don't have enough examples in our test to show what was actually required. Systems like this get increasingly difficult to maintain because if I need to add an item type, and that is after all the point of this exercise, then I might need to go and look up in a requirements document or ask a customer which of these two implementations results in the correct behavior with the new item type. And this is one of the reasons to like TDD. That had this software been developed with test-driven development, there would have been a better chance of a test showing the intention of this behavior when this coercing should apply. I'm going to undo this back to the previous implementation, which came about because of Dimitri's refactoring. And it's worth pointing out that we can only ask this question because that refactoring put the software into this nicer state where we can see that we have a problem. Again, thinking about expression, what other important thing isn't expressed in this code? I'll wait for a moment while you think of your own answer. Well, for me at least, the answer is the type of items. At the moment we have items names, but we don't have the idea of a type. In fact, our requirements doesn't mention type at all, except that the previous developer Leroy was a no-nonsense type. But that seems to me a conversation that he should have had with the people commissioning the system. Are there other types of concert tickets? What about other types of cheeses, and so on? We know from down here that we're going to add conjured, but is conjured a type of a thing, or is it the name of a thing? Can we have conjured brie? It's adding a conjured item that brings us onto the open-close principle. That says that software should be open to extension, but closed to modification. Another way of looking at that is if we only want to add functionality, we should only be adding code. We should be modifying as little of the existing code as we can. At the moment, to add a conjured item, I know that I'll need to change the degrade method, but I also have to consider the age method, where the conjured items age the same as everything else. So even in this simple system, there are two places where I need to potentially modify our software in order to extend it. So with this in mind, I'm going to add an item type. I'm going to make an enumeration class for now. And the types that we know we've got are brie, passes, sulfurous, and other. And to save scrolling up and down, I'm going to put this in the other file for now. Now I'm going to start playing with some of this logic. I'm going to change this into an if, and this one too. And now I'm going to make functions out of these. So this is brie, and this is pass, and this is sulfurous. And that should pass all our tests. And for some reason, IntelliJ has missed this here, because that is sulfurous. Good. Now, using those functions, I'm going to write the code that gives us an item type for an item. So that's item type. And this is when this is sulfurous. I want to return sulfurous. And we'll just have to make these public to make this work. When this brie, we're brie. It's a pass. Then we're a pass. Otherwise, we are other. Now that code is unused, so the test should still pass. Good. And I'm going to inline these to make use of the test against the name. But just here. And now back over here, I'm going to re-implement these in terms of the type. So this is going to be that my type is sulfurous. This is going to be passes. And this one, brie. Now that is a change to our code, so let's run it. And it still passes. And now these methods' work is done and I can inline them again. And run the tests. Good. I'm just going to take this age out of here and move it up here so we can see the next change. What we're going to do is we're going to take this type and make it a parameter to item age. And now we're going to make the receiver a parameter as well. And you can see that one call here has been updated, and now we can make the item type the receiver. That means we're going to the item, we're calling type on it, and then we're asking the type to age the item. But now item type is a class that we own, and its only job is to do this. So we can take this out of here and make it a method rather than an extension function. And it will be public. And run the test to check that's all okay. Wonderful. And now that we have a method, we can use polymorphism. As with Java and Kotlin, instances of enumerations can specialize behavior. So we can, in fact, specialize sulfurous here, and we can override the age function. And for now, I'm just going to copy this code. And to make it compile, we need to make age open. Let's check that didn't change the behavior. Good. Now IntelliJ isn't clever enough to see it, but in sulfurous, this is always sulfurous. So that this test is true, and we can remove it. Also, for anything but sulfurous, where the base function will be called, this is false. So we can remove it. And with luck, the test will show that's true. Good. Now, enumerations aren't very common in Kotlin, and this nesting gets confusing quite quickly. So let's convert this to a sealed type hierarchy. That would mean that item type was sealed, and we had instances which were objects. So we'd have an object free, which is an item type, and the same for these. And now these nested bits aren't required, and we just have to fix up the compile. And here, we'll check that does the same thing by running the tests. And it does. Now we can turn our attention to this degrade. If we return the if to a when, and add in here the type other, this is another when. Now this doesn't compile because this when isn't exhaustive, and the reason for that is that we're not using the subject type subject here. We can fix that the long way around, which is to put in an else here, and then IntelliJ will suggest that we could make type the subject, and when type is the subject, we don't need the else. Fix this when up to look like the others with an if, and check that that passes the test. And it does. Now we can either take the whole of this functionality and move it onto type, or we can take just this expression. And I think for now I'm just going to take this expression. So I'm going to say this is the amount of degradation, and then make the type the parameter, and swap the receivers. And again, the call side has been fixed up. Now we can take this and make it a method on item type, and run the tests. And now if we make degradation open, then we can start taking this behavior and moving it into the subtypes. Run that and it should pass. Good. This expression here. Passes. And then finally sulfurous is 0. And that means that all we're left with is the other. So these can go, as can the when. And now I think we might as well move degrade to the type as well. So circle dance. Like that. And that leaves these two lines here. I think we can do the same thing with. That seems to have lost its receiver for some reason. Putting it back allows us to make it. From there. And then that is our fundamental operation in here, which allows us to make this protected. And this. And this. And in fact, that could be private. And let's run again. Good. Okay, I've just had a little tidy up, moving item type out into its own file here. And also I noticed that degradation was running the wrong way, so I've made degradation positive for normal items and negative when items get better. Let's just remind ourselves how the scheme we've come up with works. When we want to update, we go through every item and ask it to update. Well, we don't actually ask it to update. What we do is we call an extension function update. And that says, let's go and get the type and ask that to update the item, passing it the item. Type is an extension property, which looks at the name and uses that to pick a particular subtype of item type. And item type has this fundamental operation of update item. And it divides that into aging and degrading. And it allows its subclasses to override what it means to age, so that sulfurous can not age. In fact, if you look at this, minus equals 0 is just the same thing as no op. And degradation, that isn't an open function, so that our subclasses can't change how degradation happens, and they can't change the fact that this coerce happens, but the subtypes are allowed to change how much an item degrades. The standard is 2, 1, but brie and passes and so on have other policies for how they degrade. And by controlling which of these methods are public and which are protected and which are overridable or not, we can express the things we found out about domain. So for example, had it only been sulfurous that didn't want to degrade at all, we would have a protected function here that sulfurous overrode so that it didn't degrade, rather than specifying its degradation was 0 and having that feed back into this policy here. So in a way, because we haven't been able to modify item, we'd have to implement the first part of an object-oriented system ourselves. What normally happens when we call a method on an object is that the runtime looks up the class that object belongs to in order to find the implementation of that method. Here, we're doing that manually. We're saying we'll do our own lookup of the type, and that will yield the code that defines the behavior. Now let's see what it would take to implement a conjured item. Well, a conjured item just needs its own item type. Could build object conjured, which is an item type. And we know its aging is going to be normal, so we don't have to override that. But the degradation is going to be twice that normal item type, so we need to override that. And in this OO system, the normal degradation is just the one that we inherit from item type, and we're already getting that here. That's super degradation for item. So we can implement conjured just by multiplying that by 2. Now that object is unused, which is a clue that we need to add it to our when statement here. And in particular, it's conjured manna cake. We're going to take that in here, and that will give us a type of conjured. And if we run that, our approvals will fail. You can see that our manna cake is now degrading twice as fast. It goes to 4, and then 2, and then stays at 0. If I update the test, zero. That's then our expected behavior. Run it once more. And we're done. Another question we might want to ask ourselves is whether this should be a sealed class now. There aren't any places anymore where we use a when and need exhaustiveness. So I think we could reasonably just make this a class open to extension. Now at the moment that's a bit moot, because if we add a different item type, we still have to change this code here. But we can imagine that lookup being part of the gilded rows, and people anywhere in our system being able to define their own item types and add them to a lookup table held in gilded rows. If you're a functional programmer, this lookup of item to type might be saying type class to you, and here we have an implementation using Kotlin's new context receivers. So we define an interface of item type provider, and we put the conversion on here. Now by saying that item update requires this item type provider, that operation is available in here. Our update can also say that it requires the item type provider. And now in order to call it, an item type provider has to be in scope. We can do that in the test over here by creating an item type lookup and then saying with this type lookup, we call gilded rows update. If we commented out that with, then it wouldn't compile because we don't have a context receiver. What does our item type lookup look like? Well, that's here, and it takes names and the item type. So sulfurous goes to sulfurous, aged brie to brie, and so on, and it finds the first of these pairs where the name matches and returns the second. But context receivers are a sneak peek and probably not ready for production use, so let's return to the previous version. This lookup also means that we have a more sophisticated policy based on the name. So we could just contain sulfurous. And maybe starts with, in order to work with other bands. Also, item types don't have to be objects. We could create class passes, which is an item type, and that can have its own properties, which it uses in degradation. Using this, passes is -1, -2, -3. Check that's true. But that seems to have broken the compiler. Let's try rebuilding from scratch. Well, there we go. Sad, isn't it? But I didn't want to show you how IntelliJ doesn't work. What I wanted to show was that we could then say things like, this way we can have even more code to reuse, and if we wanted to, we could even parse numbers out of this name string or somewhere else in order to establish the parameters to our item type. We don't actually need that behavior yet though, so I've undone it, but it's good to know that it's a facility that we could implement if our customer wanted it. There's a lot of backlash against objects at the moment, but the fact is, for problems like these, classes and subclasses are excellent for defining commonality and differences in behaviors. And that's what we often need to capture our knowledge about the domain as we gain it by writing the code. It's that knowledge captured in the code that means that our systems can get easier to maintain over time rather than harder, because they will, if we're diligent, naturally become structured so the sort of changes we need to make are easy. As engineers, our job is to strike a balance between over and under designing a system. We want to keep it simple, but at the same time not so simple that it doesn't express the things that we've learned about how it should be and how it needs to evolve. Well, I hope you enjoyed this. If you have, please subscribe to the channel, and if you haven't already, check out my series on implementing the Gilded rows from scratch. It ends up with an item type solution that is similar to the one we saw today, but is significantly more functional and I think slightly more versatile. Thanks for watching.